Okay, continuing on with class 22, here is an example. This is a problem out of Munson's book, and it says water flows steadily through a 3/4 inch diameter galvanized iron pipe, and the flow rate is 0.02 cubic feet per second. Your boss suggests that the friction losses in the straight pipe sections are negligible compared to the losses in the threaded elbows and fittings of the system. Do you agree or disagree with your boss? Support your answer with appropriate calculations, as opposed to inappropriate calculations. Okay, so I think I'll start off by finding the air velocity of the pipe. So this is 3/4 inch pipe, and they're saying it's 3/4 diameter. I'm instead going to call it nominal pipe size, 3/4 inch nominal pipe size. So the OD of that is 1.05 inches. The wall thickness for schedule, let's call it scheduled 40. So schedule 40, the wall thickness is 0.113. So the ID is just 1.05 minus 2 times 0.113, and that should get us 0.8240 inches. We were given that the flow is 2 cubic feet per second. So let's find the velocity. This is that flow rate divided by the area. So 0.02 and divided by, let me go pi over 4. Just the people talking in the offices next to me is really distracting. I'm going to turn this into feet, so I'm going to 0.824 divided by 12 squared. So we get 5.401 feet per second. Good thing to do right away is get the Reynolds number. I'm going to use this version of the Reynolds number where we use nu instead of using the density and mu. So we use the kinematic viscosity instead of the density and the dynamic viscosity. So here's our 5.401, and here's our diameter 0.8240, but we need to get it into feet, so divide it by 12. And looking up this kinematic viscosity, we find it's 1.21 E minus 5. So what we're left with is 30,650, and that is greater than 4,000. Therefore, it's turbulent. They told us that we are going to use a galvanized iron pipe, right? And based on, based on this information I provided in class 21, we have a galvanized pipe. We can use 0.0005. And I left out a 0. And these are feet, by the way. So because we want to have our epsilon over d, so our roughness, or 0.0005, divided by our diameter of 0.84824, divided by 12. So we're left with 0.007282. So we're going to try to find that from the Moody diagram. So now that we have the Reynolds number and this, those are both dimensionless values, we can come back up to our Moody diagram. Let's see how good we can do. 0.000, let's see how many zeros did I have into there. Only had 2 zeros. So we're really going to be somewhere in between those two. And we had 30,000. So that 30,000, here's 20,000, here's 40,000 right there. So here's what I'll do. I like to grab a hold of this just as I'm trying to think, and I use my Microsoft Paint a lot, and right through here, and so like I'm like right there. I'm gonna say that that's like 30,000. Try to make this straight, and I'll make it. I'll go small. There you go. So somewhere in there, I can't quite tell. And then, what did I say? Somewhere in here, because I had somewhere between, somewhere in there. Right, and you can see that I'm kind of like in this transition area. Right, so somewhere in that way, somewhere right in there. Let's see how good I did. Let's see how good I can do. So I'm going to say here's 3. So I'm going to guess that's 3, 2, 3, 4, 3, 5, 3, no, 2, 4, 6, 8, right? So I'm somewhere right in here. So 0.0, like call it 0.035, right? That was my guesstimate. But I can also, for the Darcy friction factor, but I can also use the equation that we introduced in the last class somewhere. No, it's somewhere in here. There we go. This guy right here. We're going to introduce this. We had this equation right there, which I think we call it the Halland equation. And if we do that, that equation is an approximation, but it's a pretty decent approximation. We go negative 1.8 times the log base 10 of the ratio over here, or 0.007282 divided by 3.7 and raised to the 1.11 plus 6.9 and divided by the Reynolds number, 30,650. And then we take that whole thing, right? So I close that out to the negative 2. And I got 0.03633, all right? So I had said 0.035. This isn't terribly off. I'm going to go ahead and use this one. It's still an approximation because this is not the Moody this is not exactly matching with the Moody diagram, but it does a pretty good job. I've graphed them on top of each other before, and they don't look too bad. All right, so now let's figure out what the piping losses are. So the total length of this thing, we're going to have 6 inches plus 6 inches plus 4 inches plus 1 inch. Right, we're going to see if that matters. Divided by 12. And we end up with 1.417 feet. And now let's see what the head losses are. And remember, we call the piping losses the major ones. Even if they're less, I'm going to call them. And there's F times the L over D times V squared over 2G. So in our case, we got 0.03633. The length of it is 1.417. The diameter, 0.824 divided by 12. It's got to be feet over feet. And then the velocity squared, so 5.401 squared divided by 2 divided by 32.2. And what we'll end up with is 0.3396 feet of head loss. Let's figure out what the head losses are due to the fittings. So we take a look here, and let's do elbows. We have two elbows, and each elbow, as you'll recall, each elbow is these are threaded 1.5. we have a branch. We're going through a branch too because we're going up this way and coming back that way. So we're going to have a branch, and if you'll recall, a branch was branch flow threaded 2.0. And then what else do we have? Oh, we also have a change in diameter right here. So we went from 0.824 and went to 0.6. So in order to get that, we have to go back to this. And so we went to A2 over A1. I'll write it over to the side, A2 over A1. And we don't need to change units or even use the pi over 4. We're just going to go 0.6 squared over 0.824 squared. And we end up with something like 0.5302. I'm not sure I did a great job of picking off this graph right here, but we're somewhere in the middle, right in there. And I decided that was at 0.25, right? Because there's 0.3, so 0.25 maybe. It might be a little lower right in there, but let's go ahead and put it. So I decided that was going to be 0.25. So we added all those up and we get 5.25. And now we go for the minor losses. That's the sum of the KL times V squared over 2G. So we get 5.25 times 5.401 squared divided by 2 divided by 32.2. And what we end up with is 2.378 feet of head loss. So now we're going to say, well, what is this negligible? Is really what the question was to your boss. Is it negligible? And so I would say, let's find out what the percent of major losses of the total head loss, right? So we can take a 0.3396 and 0.3396 and 2.378. And what you end up finding is a 12.5%. So I don't think that's negligible. The boss was saying he felt that this amount was, you could just ignore that. And I think 12.5% is not negligible. So I'm going to say nope. Not negligible. But it is a bit of a matter of opinion. I think anything that would be like 5% or less is negligible. But, anything that starts to approach 10, I think you need to keep that in mind. I don't think you can just discount it. So that's the first of the examples. Let's do some more after this in the next video.